Picture this for a second. Your computer's processor isn't just some cold, static square of silicon. No, it is a bustling, unimaginably complex microcity. We're talking about a metropolis where millions of workers communicate perfectly, shuttling massive amounts of cargo down dedicated multi-lane highways. And the craziest part? The whole thing is synchronized to a relentless heartbeat that pumps billions of times every single second.
Okay, let's dive right into this explainer. What you're looking at here are the metallic foundations of our microcity, the intricate pathways of the motherboard and processor architecture. To really grasp how your device manages to do, well, literally everything, from rendering a 4K video to crunching massive datasets, we need to zoom all the way in and look at the core rules running this digital landscape.
Now, this architecture is super dense, so we're going to break it down into logical, easily digestible neighborhoods. We'll start with the fundamental blueprint, step on to the factory floor, trace the system highways, see what pushes performance to the limit, feel the heartbeat of the operation, and finally, check out how the city handles emergency traffic control.
Right, so let's kick things off with part 1, the blueprint, or the von Neumann model.
Every great city needs a master plan, right? Well, for computers, that plan was actually drafted way back in 1945 by John von Neumann, and almost every modern computer still uses his exact model today. The absolutely crucial thing to remember here is his core set of rules. You have to have a central processing unit with direct access to memory. And this was the real game changer. That memory has to contain both the stored program and the data it needs. Then, the processor executes those stored instructions sequentially, one right after the other. It sounds simple, but that sequential processing is what unlocks pretty much endless possibilities.
Moving right along to section 2, the factory floor, inside the CPU. Let's head to the active center of our city, the central processing unit. Think of this as the main factory floor where the actual heavy lifting gets done. You've got two main workers down here. First, the arithmetic and logic unit, or ALU, which handles all the math and logical decision-making. And right above it, calling the shots, is the control unit. The control unit is the ultimate orchestrator. It ensures every instruction is handled perfectly and directs the flow of data using these vital internal clocks to keep everyone in perfect sync.
Placed right alongside those workers, we have registers. Now, registers are ultra-fast, temporary storage lockers, but they have a really limited capacity. If your processor only has one general-purpose register, we call it the accumulator. This little locker stores a single value that the ALU is about to process, and it's also the exact spot where the ALU drops its finished calculation right after it's done executing. Alongside the accumulator, we have a few special-purpose registers too. Meet the program counter, or PC. You can kind of think of the PC as the factory foreman. Its one and only job is to hold the memory address of exactly where the very next instruction needs to be pulled from, so it always knows what the next step is, no matter what. Next up, a very dynamic duo, the memory address register and the memory data register. The MAR stores the location in memory that we're about to read from or write to, while the MDR handles the actual data itself. The big takeaway here is that the MDR acts as a totally vital buffer. Why? Because the data moving around inside the processor is moving wildly faster than data transferring outside of it. Without that buffer, the whole system would just overwhelm itself and crash. To wrap up our factory tour, we've got the current instruction register. That one holds the current task while it's actively being decoded and executed. And finally, the status register. Instead of holding a complete number, each individual bit in the status register acts as an independent flag for specific conditions, like if a math problem had a carry or if there was an overflow error. It's essentially the factory's warning light system. Okay, section 3, the highways, otherwise known as the system bus. Now that we know how the factory works, let's step outside and see how the data actually gets around town. It travels on parallel wires collectively called the system bus. But we've got different types of highways here. First is the address bus. This one is literally a one-way street. It only ever carries addresses from the MAR out to the memory or to your devices. It never brings an address back. The data bus, on the other hand, is a bidirectional, two-way highway. It's constantly ferrying the actual data and instructions back and forth across the system.
To keep these highways from turning into a massive traffic jam, we use the control bus. This is an 8-wire road that transmits timing signals to keep everything synchronized. And when data actually needs to leave our microcity entirely, it goes through an input-output port, like a USB.
USB is brilliant. It acts as this massive external shipping dock that can support up to 127 plug-and-play devices, all neatly organized into a hierarchy.
Moving on to Section 4, pushing system performance.
So, what actually makes this microcity run faster and more efficiently? Well, there are a few key speed factors. First is clock speed, which sets the absolute shortest time any single action can take. But since external components drag things down, modern systems use multi-core processors. That is essentially building multiple CPU factory floors so they can work in parallel. We also add cache memory, which is insanely fast storage built right onto the chip itself. And finally, there's word length, usually 32 or 64 bits. The larger the word length, the wider those data highways are, meaning way more data can travel at the exact same time.
All right, Section 5, the heartbeat or the fetch-execute cycle.
All of this incredible infrastructure relies on a rapid, thumping heartbeat to keep it running perfectly. We call it the fetch-execute cycle. It is beautifully simple, but it happens at just mind-bending speeds. Step 1, fetch. The instruction is grabbed from memory. Step 2, decode. The control unit analyzes it to figure out what actually needs to be done. And Step 3, execute. The ALU or other parts are fired up to actually do the job. Grab it, figure it out, do it. Over and over.
Following this logical flow, there is a super cool detail to notice during the fetch stage. While an instruction is actively being loaded from memory into the MDR, the program counter is simultaneously incrementing by 1. So our factory foreman is already pointing to the very next task before the current one has even finished arriving. Talk about efficiency.
Now, if you look at this process in its raw form, it's written in registered transfer notation. Okay, I know, it looks like alphabet soup, but let's demystify it really quickly. The arrow just means is transferred to, and the square brackets literally just mean the contents of. So, line 1, it just says the memory address register gets whatever is inside the program counter. That semicolon on the next line means two things happen at exactly the same time. The PC ticks up by 1, while the MDR grabs the data from the address we just set. And finally, the CIR grabs that instruction from the MDR. See? Not so bad. So, we've got this perfectly sequential, endlessly repeating machine. But let me ask you this. How does a machine that can only do things one by one, exactly as it was programmed, handle a sudden, unpredictable event, like a hardware fault, a user violently clicking a mouse, or a total fatal error?
That brings us to Section 6, traffic control, or handling interrupts.
Interrupts are basically the city's emergency dispatch and dynamic traffic control. Here's how it plays out. The processor doesn't just abruptly drop what it's doing. At the very end of every single fetch-execute cycle, it checks its flags to see if an interrupt was generated. If there is one, it takes all its current register contents and saves them safely away. It's like hitting pause and saving your game. Then, it loads an interrupt service routine, or ISR, handles the emergency, checks if there are any other fires to put out, and if the coast is clear, it restores all those saved registers and goes right back to the original program, exactly where it left off.
Everything we just unpacked, the rigid blueprint rules, the registers buffering crazy amounts of data, the bidirectional highways, the simultaneous fetching, the complex interrupt checks, it isn't just computer science theory. The very next time you tap a screen or hit a key, just take a second to realize that this entire micro-city operation is happening flawlessly billions of times a second, inside the device right in front of you. But it kind of makes you wonder, if this is the dizzying complexity required from just a standard CPU, what on earth does the microscopic metropolis of tomorrow's AI supercomputers look like?